Welcome back, everyone. We are continuing our discussion about solving integrals involving u-substitution. And we're going to begin with two review problems, and then we're going to do one unusual example, something a little bit, something we have not seen before, where degree of the top is higher than degree of the bottom. But before we get to that one, so I'm going to show you two examples. So one of them is the integral from 0 to 1 of 4x dx divided by the square root of 5x squared plus 3. And then the other one we're going to solve is the integral from 1 to 2 of 4x dx over 5x squared plus 3, no square root on the bottom. So I'm doing these two problems back to back because I want you to remember things that we've learned in the previous section, 3.3a and as well as 3.3b, and how important it is to recognize what type of u-substitution problem this is and how you're going to solve it. So let's take a look at both of them. So starting with this one. So first of all, can this question be done with u-substitution? So at a glance, you can think of it of, okay, u being the inside of the square root, 5x squared plus 3. Its derivative is 10x dx. There is already an x dx in the numerator, so you know this is going to work with u-substitution, right? Okay, so let's get started. So let u be equal to 5x squared plus 3. So its derivative du is 10x dx. And ultimately, we're going to need to know what x dx is. And therefore, solve for x dx over here. Divide both sides by 10. So x dx is du over 10. So keep that on the side, right? As we try to write this integral in terms of something that only has an integral that only has u's in it. So this 4 can be factored outside. At the moment, ignore that 10 down there. Okay, so the denominator here is going to be the square root of u. And instead of x dx, over here we determine x dx is du over 10, right? So x dx will be replaced by du over 10. So I usually put the du on the inside, over 10 on the outside. So that's what you see over here. The 1 over 10 came from that. So the 4 was pulled outside. X dx is replaced with du over 10. Du is placed on the inside, over 10 part on the outside. And this entire denominator became now the square root of u. So now that we have that, let's see how we can solve this integral. Notice I'm putting dot, dot, dot on the limits of integration because the moment you have your integral in terms of the u variable, those limits no longer apply. Those were set for the x variable, so we're going to wait until we bring the x's back before we plug the values back. So those limits of integration will have to wait until the x variable comes back. So to integrate this, let's just put it up as u to a power. So that'll be u to the negative 1/2 power. And we can also simplify 4/10 is the same as 2/5. So now we're going to be integrating it u to the negative 1/2. So apply the power rule of integration. Notice for something like this, you don't need natural log function, right? Because natural log function only works when you have 1 over u du. That is very, very important to remember. You cannot have like natural log of square root of u. That such a rule does not exist. Something like this has to be taken care of with the power rule of integration, meaning put it up as u to a power, apply the power rule, add 1 to the power, you're going to get 1/2 u to the 1/2 over 1/2, or times 2 over 1. So that's what I have here. Still the dot, dot, dot. We're going to bring those limits back momentarily. So now I have 4 over 5 times u to the 1/2. And again, the limits are still not brought in because still we have the u in there. So let's get rid of the u. U being equal to 5x squared plus 3. So go ahead and bring it in. So it'll be 4 over 5 times 5x squared plus 3, quantity to the 1/2 power. In other words, square root of that quantity. So now that it's brought in, now we can bring the limits of integration because those were set for the x variable, and now that we have the x variable back, we're ready to put the limits in there. So the limits are from 0 to 1. So that's what I have here, and all we have to do now is plug in the upper limit minus plug in the lower limit, and when you have a constant like this up front, you can actually keep that outside. So plug the 1 in there for x, you're going to have 8 to the 1/2, and plug the 0 in there for x, you're going to get 3 to the 1/2, or square root of 3. And the 4/5 is kept on the outside, just to make things simple. You could have, of course, said 4/5 root 8 minus 4/5 root 3. That would have been fine, and then factor the 4/5 out if you like. You can definitely leave the answer like this. I always prefer the exact answer, but you can also check, sometimes maybe you're checking the answer is given to you in decimal form, you can always convert it to check, and it turns out to be 0.877. So a u-substitution question where we had to use the power rule for that one, right? Okay, take a moment, see if you have any questions. If so, jot it down so you can ask me during class if you're in my face-to-face, one of my face-to-face classes or live online classes. Now I'd like for you to think about the second problem I have near the bottom of the page there. Let me separate it from everything else. So it looks very, very similar. It is going to be a little bit different the way we solve this one, right? So this looks the same, but there's no square root around the denominator. And the numbers are different, integral from 1 to 2. All right, so do you think u-substitution is going to work here? So for the same reason we discussed above, u-sub is going to work, and the same u works, right? Let u be 5x squared plus 3, so that du equals 10x dx. And again, we're going to need to know what x dx is. So divide both sides by 10. So x dx is du over 10. So let's keep that on the side for the moment. So the 4 will be taken outside. X dx will be replaced with du over 10. And just like above, the 1 over 10 part can go outside. And now what do we have on the inside? So the x dx has been taken care of. 4 has been taken outside. So denominator now is what we would call u to be. So again, remembering that x dx is du over 10. So you can have a du inside the integral sign. And the bottom is just what we call u to be. So du over u. Notice for the limits of integration, I'm just putting dot, dot, dot at the moment because we're going to bring those back in when we bring the x variable back into our problem. Now, how do you do something like this? The integral of du over u. Can you use the power rule here? Well, you could try. You could say, okay, u to the negative 1, add 1 to the power, u to the 0, divide by 0. Okay, wait a minute. We notice it's undefined, right? At that point, that might be a reminder, okay, there was another special rule for this, right? It only works when you have 1 over u du. That's when you have the natural log of u, right? The integral of 1 over u du. So it's going to be 2/5 times ln of the absolute value of u. Again, the limits are going to be replaced in a moment. When we bring the x variable back, we're going to put those in there. And u being 5x squared plus 3, go ahead and put that in place of u. And now we can bring our original limits for x from 1 to 2. And as always, to evaluate this, we're going to plug in the upper limit minus the lower limit. And a few things I'd like to point out here. For example, over here you had to keep the integral sign because here we had not yet taken the integral. So you want to keep that in place. But in the next step, once you take the integral, that sign should disappear. It would be wrong for me to put here another integral sign, right? That's simple but important thing to know about notation. And also, when you're plugging limits, the common notation is you put the line right there. Sometimes I see people putting a line there and stuff. It's just, you're expected to follow proper standardized math notation. So the line should be at the very end here from 1 to 2. It should not be an integral symbol. It should be a line because we have already taken the entire derivative, right? We are doing the evaluating it. And this line means we're going to evaluate it. Okay, so let's plug it in. 2 squared is 4 times 5, 20 plus 3. So 2/5, which can be factored outside. When you plug in the upper limit, you're going to have ln of 23. And I'm plugging the lower limit of 1. 1 squared is 1. 5 times 1 is 5. 5 plus 3 is 8. So ln 23 minus ln 8. Now you could leave it like that, but it would be nice to know the properties of logs, that ln a minus ln b is ln a over b, right? At that point, you can write it as ln 23 over 8. And don't forget the 2/5 on the outside. And of course, you can also convert that to a decimal. So you can also leave the answer as 0.422. So either one of these would be okay. Even this one would be okay. But I think it's good for you to know how to manipulate logarithms and how to write them in the simplest possible form, such as this one. You're going to see that again in other classes if you're taking Calc 2 and beyond. Now, I also want to show you one more way to solve an integral when you have limits of integration with u-substitution. So here we waited for the x's to come back, and that's when we used the original limits there, right? But it was also possible to take it from this step when you have already taken the entire derivative. 2 over 5 ln u. What you can do is you can actually change your limits and change them from the limits for x to to limits for u. So if your x is 1, okay, if your x is 1, I'm going to plug in 1 in here for x. What do you get for u? 1 squared is 1, 5 plus 3 is 8, right? So the lower limit, when x is 1, u is 8. So if you're going to plug the limits with the u variable in there, you need to plug it, the lower limit has to be 8. On the other hand, if x is 2, remember x is going from 1 to 2, right? So go ahead and plug in 2 in your x, where you have u equals 5x squared plus 3. So if you plug in a 2 in there, 2 squared is 4, 4 times 1 is 20 plus 3. So the upper limit is 23. So what we're saying is it is okay to plug the values in when you have the u's in there. However, you need to change your limits of integration, okay? So basically what we've just done is we went from the x limits to u limits. Remember, u was 5x squared plus 3. And if x is equal to 1, this one turned out to be 8. If x is 2, this is 23. So instead of going x from 1 to 3, you can go u from 8 to 23. X going from 1 to 2, u going from 8 to 23. So that's what we have here. Okay, so it's okay to plug the limits for u, but you must change your limits, and they have to be set for the u variable. So at this point, if you plug in upper limit minus lower limit, we're going to get the same exact answer as we got in the previous approach to this problem. So I want you to know both of these, because I've noticed that like sometimes physics professors, they like to use this approach, using the limits for u. So I don't want you to be confused. And if they're doing it with that method, I want you to be able to follow it. So whichever method your next professor uses in Calc 2 or physics classes, you should be able to follow it. And as you're solving it, you have a choice. If you're going to use the x variable, keep the original limits. If you're going to use the u variable, switch your limits to the u variable. I personally like this approach better because I've seen too many students making mistakes. So I like to bring the x's back and plug it in there, but it's completely up to you. All right, I'm going to do one more example. And this one is going to be a little bit of an unusual problem. Okay, so this is going to be the integral of x cubed plus 1 over x minus 2. X cubed plus 1 over x minus 2. So for this question, you might say, okay, what am I going to let u be? You let u be x minus 2, the u equals dx. What am I going to do with that x cubed up there, right? If you let u equals x cubed, the derivative is 3x squared. Again, I don't see an x squared dx. So it looks like our typical methods that we've been using do not apply here. In that situation, what you should be doing is long division. And how did I even think about that? Well, this technique works, the long division works when the degree of the top is higher than the degree of the bottom. It even works when it's equal to the degree of the bottom. So if it was like an x cubed over x cubed, or if you had the degree of the top is higher than the bottom, then you can use this approach. In this case, it's higher. Okay, so how does it work? We need to take the, first of all, we need to do a long division. Divide x cubed plus 1 by x minus 2. So literally we're going to do long division. So we'd ask ourselves, x goes into x cubed how many times? Think of it this way. You're just dividing x cubed over x. And the answer should be x squared times, right? So you're going to put x squared up here. But whatever you put up here, you need to multiply it by both of these two terms. So x squared times x is x to the third. And then you have x squared times negative 2 is negative 2x squared. Now let's subtract. And to subtract means, okay, so we're going to do negative 1 times the whole quantity, right? So you should distribute the negative. So it's going to be basically, the first one will be negative, the second one will be positive. And if you add x cubed minus x cubed, they cancel. That's always a good sign. You want the first ones to cancel when you're doing long division. And then 1 plus 2x squared is going to be just 2x squared plus 1. Now we're going to ask the same question again, okay? So x goes into 2x squared how many times? Think of it this way. 2x squared over x. And if you said 2x, you are correct. So put the plus 2x up there. Now the same thing, 2x times x minus 2. Do it one by one. 2x times x is 2x squared. And 2x times negative 2 is negative 4x. And again, to subtract, this become negative, this will become positive. And now you add, so 2x squared minus 2x squared, they cancel. 1 plus 4x, or 4x plus 1 is what we have left. One last time, we're going to do the same thing, okay? X goes into 4x how many times? Think of it this way. 4x over x. That's 4 times, right? So put the plus 4 up there. Multiply 4 times x minus 2. It'll be 4x minus 8. And to subtract, change all the signs to their opposites. So this one becomes a negative. This one becomes a positive. And the 4x is canceled, so now we have plus 1 plus 8, which is 9. Okay, so we did a long division. X no longer goes into 9. This is our quotient. And the way you would leave it is you would say, okay, this over that equals the quotient plus remainder over divisor. So plus 9 over x minus 2. Okay, so the given problem is the same as integrating this whole quantity, x squared plus 2x plus 4 plus 9 over x minus 2. Okay, and now let's integrate it term by term. This one is going to be x cubed over 3. This one is going to be 2x squared over 2. And this one 4x. And 2x squared over 2, you can cancel the 2's there. What are you going to do about this part? The part about 9 over x minus 2. Think about it for a minute. If you said you should do a u-sub there, you are correct. You would do like u be x minus 2. Ultimately, it will look like 9 over u du. And you're going to need a natural log function there. So you can do that a little bit with detail on the side. That will be 9 times natural log of x minus 2 plus c. So now you see why we left this problem all the way to this point in the semester, because you couldn't have done this problem unless you knew how to integrate something like 1 over u du with a natural log function. And since we've just recently learned that, so now you can do problems where degree of the top is higher than degree of the bottom, especially when you're dividing with a linear term like that. Okay, and if you're a little bit rusty about long division, you can search long division in YouTube, see another example about that. And you are not alone. From past experience, a lot of students, when they do long division, they haven't done it in a long time. They're a little bit rusty on that. But once you do like 1 or 2 problems, you're going to be fine. Just go one by one, like the leading term here goes into the leading term there. How many times? Whatever you get, you put it up there, and you're going to, whatever you write up there, it's going to be multiplied by all the terms of your divisor and written out right underneath it. Again, so it may take a few more problems to gain the confidence there, but if you like, close this one again, do it on your own, see if you can do the entire long division step by step without looking at your notes this time. So that would be helpful. So just to recap this problem, we did long division just to rewrite it, right? But that was not the entire problem. The problem was to integrate it. So many times I see in a problem like this, students leave it like this. They say, okay, done. No, we're not done. We just did long division. This is equivalent to that. But to integrate, you still have to go one more step, right? Integrate piece by piece each of those 4 terms. All right, so when we come back, we're actually going to take a look at the next section.